started with this review because we have this room scheduled for an hour. We're actually recording the review by request of many students that sometimes can't make these reviews. So what that means is we're just going to do this a little bit different. We're not going to be able to screen as many questions because we kind of have to get through the material we're doing. So we don't have a video posted that's a full hour long, but rather maybe 45 minutes. That way you guys are able to go back and re-watch what we're going to do and the problems that we've created for this exam. So if you do end up having questions that we couldn't answer during the filming or during this process of the review, once we're done with what we've got, we're going to do like a question and answer system, and if you have specific questions, just bring them down at the end and we can work out a particular problem that you might have, okay? That also means that we would ask that you guys could just keep the chatter down a little bit. We know that when we're talking about problems, you should be talking with your neighbor about it. Trying to figure out how to solve it, what you need to do. But we'll just try to keep that noise level down so that in the video later on when you go to watch it, you can hear Corbin and I's voices and you can kind of hear what's being said and what's going on. So let's do a little introduction about this exam. So this is our first free response exam that we've had in this class. I know that to some of you that's a little bit scary, free response exams. Some of you love them, some of you don't. From personal experience, I know that these free response exams are very fair. The nice thing is there's no material on this exam that hasn't been tested previously by multiple choice. Meaning we're not going over equilibrium things that we're talking about now in class, but just chapters 13 and chapters 21. So that means kinetics and radioactivity. So you can rule out Raoult's law, vapor pressure, and all those things we talked about in chapter 11 because that will not be on this free response exam. So that cuts your study in half, meaning you get to focus more on these things that are going to be on this exam. Let's see, does anybody have a particular question about the exam right now that we can answer? Yeah.
Do you know how many questions it might be?
So the exam should be 18 questions long, right? A multiple choice exam takes people on average about 50 minutes. Some of you about 40 minutes. It's right around there. The free response exam will take you probably 20 minutes longer than that. And that's on average. So if you're a person that you know you take exams a little bit slower, the free response is an exam you want to give yourself a little bit more time for. That is because on the multiple choice exams, from what you guys have experienced, a lot of the questions were very calculation based, meaning you were actually plugging in numbers. You were actually solving for values and integers. On these free response exams, Dr. Macedoni generally likes to question you about some of the conceptual things we've talked about or the principles that we've gone over. So that means just knowing the equations, maybe knowing how to solve for the numbers isn't quite enough for these free response exams. You're going to want to go through your book, go through your notes, and any of the chapters we've read in our book, look at all the bolded terms. Really understand those. An example would be something like mass effect, fusion, fission. Now we're going to go over those things in our review, but those are the types of questions that can be asked to maybe define something or give a brief explanation of some sort of process instead of maybe solve for a number. Now solving for numbers will be on there, but I'm saying that is something that's a little bit different. So focus on that a little bit. And that should be the exam. So any last questions about that?
The test opens and closes when?
So the test opens and closes on the testing center website, so you got to look at that. So that's Dr. Macedoni's response to that question always. So just look on the testing center website and you'll get it.
Is it worth as much as a normal test?
Worth as much as a normal test. Yeah. Okay, and I saw a question back here. Okay, right here.
Which chapters are going to be on this test?
So we said chapters 13 and chapters 21. So the necessary skills list for both of those chapters is on Learning Suite under the content page, and you're going to want to focus on those. Okay? So let's get started on kinetics. So kinetics, you guys, this is going to be the most heavily tested part of the free response exam. I think Dr. Macedoni sent out an email, and he said that the test really leans towards that. Because radioactivity, and anything we've been talking about radioactivity, is really based around kinetics, right? Reaction rates of things that are happening. So I've got a couple problems up here on the board that I've kind of derived. Now you'll notice that these are not real problems, meaning we're not using real species or real chemicals, but rather hypothetical values, letters. And so what I'm trying to show you guys is how to solve these problems, how to think through them, so that when you get to the exam and you're given real chemicals, real molecules, you already know the process that you need to do to solve that question, okay? So the first thing we need to do is kind of break up what is a rate law, how to write a rate law. So a rate law, we have rate is equal to K times the concentrations of our reactants. Okay, I'm going to put an R here for our reactants. Okay, so what is something that is really important when we're determining our rate law? Somebody give me what you think is the most important thing that tells you the most about your rate law. Up front.
The slowest, well, depending if you have multiple steps in a reaction.
Right.
The slowest step.
So with mechanisms, your slowest step determines your rate law. We're going to get to that. It's very important. How about just in the rate law itself? There's something that I think is very important in understanding that tells you a lot about your rate law.
Would it be the order?
The order is very important, right? And what I think is most important is this K value right here. Our rate constant tells us a lot about the rate law. So I have this question up here, and I'm posing this question: how to use a K value? How is that so important? We've got this K value right here, 0.001, and these units. So then I give you these reactions right here, and maybe I ask you a question. This K constant probably is a part of which elementary reaction that we have written? All right, so think that through for just a minute. We'll take 30 seconds to think this through. This K constant goes with which one of these, most likely, which one of these elementary reactions? This will help you understand why a K constant is so important, what it tells you about a reaction. Okay, let's quiet down and let's talk about it a little bit. So, what kind of tips us off? How do we know which reaction to choose? What is our indicator of our K constant, Andrew?
Wait, what was the question?
What indicates from our K constant, what indicates which elementary step that this would belong to? What is our best determiner? Is it the magnitude or actual value of our K constant?
Would it be the M? The M is the -3?
Exactly, it's our units. Our units tell us a lot about our reaction order, which rate law we're dealing with. So out of these three, we know that a rate is equal to a constant. We have our constant, hypothetically, multiplied by the concentrations of our reactants, right? So what is the units for each reactant here if we were dealing with concentrations? Molarity, right? So for this specific elementary step, we would have A, the concentration of A times the concentration of B, which would be molarity times molarity, would give me molarity squared, right? So trying to figure out why the K is so important tells us a lot about what the rate really means. So when we talk about a rate, we're talking about how fast something is occurring. Not the time frame that it took to do it, but at what speed or which rate that happens, right? So what are the units we always use for rate?
Polarity.
Yeah, molarity per second, right? So our units are molarity per second. So whatever we do mathematically here, we multiply our concentrations of our reactants times our K value. When we sum or put those units together from both, we should end up with molarity per second. So that's what I was trying to get at with this. If these are the units of my K value, right? Inverse molarity cubed, inverse seconds, then whatever I should have up here that I'm multiplying that by with my reactants should cancel out with my K constant units and give me molarity per second. So that's why I know that molarity squared on top, if I was to multiply that by this, would not give me molarity per second, right? If I look at this one, I would get molarity squared from A, right, times molarity, get molarity cubed. If I multiply that with this K constant, it would just cancel out molarity, and molarity would not be there, and I would just get inverse seconds for my rate, which is not a true unit. If I use this, I would get molarity squared times molarity again, and get molarity to the 4th power. And when I multiply that by my K constant, I would get molarity per second, right? So this would be step, or this would be the reaction that has this K constant in it. So our units for our K constant tell us a heck of a lot about our rate law that we're writing. So why is this important? Why am I bringing this up? Well, if you get on your exam and you're asked to write an entire rate law using data like we're going to do later, it's important to get the right units on your K. Your K actually matters. If you write the wrong units, then technically you're contradicting yourself with what the real rate law is, so make sure that you understand what was going on here. So for those of you who maybe aren't as familiar with when we say molarity inverse cubed here, what that means is it's the same as saying 1 over molarity cubed, right? It's the same, it's just a different way of writing it. It's just a little bit cleaner to write it like this. So that's why this one, again, works for us. So if you didn't get that, you can rewatch this video and look over again why this was the reaction that mattered the most, okay? Does anybody have any questions about that? So I know that she said reaction order is important. Yeah, exactly, because our rate constant will predict also the order. If I told you what's the order of the reaction that this must be dealing with? Fourth order, right? It would have to be fourth order so that we can get a rate that is molarity per second. So our K constant units tell us a ton about what's going on, okay? Any questions? Okay, one more thing. Let's talk about this. If I was a factory owner, and I owned a big factory, and in this factory, I was doing some sort of chemical reaction, okay? And let's say I came to you and I said, with the factory I own, with the chemical reaction we're doing, producing this chemical that we're selling, I'm having a problem. I can't seem to produce the reaction at the correct rate. I've predicted the rate at which it should be occurring, and it's not actually happening. What do you think, what are your ideas for me? What is going wrong? What would be your guys' responses to a question like that? So kind of putting some of these conceptual things into a real-life situation. I asked you, as a factory owner, about a reaction that's taking place. It's not taking place at the correct rate. What would be your suggestions? What are things that are happening?
Probably like if there's mechanisms within the reaction, like thinks it's an elementary reaction, but it's not.
Okay, so he's saying that there's probably a mechanism within the reaction. Well, that's probably not going to change much of the rate. The mechanism is still just occurring. I'm having a problem with the rate at which is occurring. I probably understood that there was a mechanism, but it's not occurring at the right rate.
There's not enough concentration of one of the reactants.
Okay, so he's saying concentration is maybe one of my problems. I'm having a problem with the correct concentrations of my reactants. That's true. So concentrations affect reaction rates. What else could be a potential problem? Andrew?
You don't have the proper catalyst?
I don't have the proper catalyst, or I'm not using a catalyst. So concentration and catalyst are a problem that I'm having. Okay, in the back?
Temperature?
Temperature. Maybe I'm not using the correct temperature for my reaction. So it's not occurring at the right rate. That's a valid one. So we have concentration, we have catalyst, we have temperature. One more.
Phase.
The phase, he says, or the physical state. So what does that mean? Well, in order for things to react, right, they must collide in a specific way, right? So if I have different phases, for instance, I'm trying to react a solid with a liquid is moving around a lot more, right? Those molecules have a higher disorder entropy. They're moving around. Maybe they don't react or collide well with a solid when it's stuck in a lattice structure. So my rate isn't happening. But if I had two liquids and I put two liquids together, they're going to collide more, and so that rate will change, right? So that's what phase or physical state, that's how that changes my reaction, okay? So remember those four things. Okay, those are very important. If you're asked a question about what are things that change reacting rates, well, you know. Remember, it's catalyst, it is concentration, it is temperature, and physical state. Okay? All right, so now we're going to kind of go over some of the things that Braden was just talking about right here with your units of your K. We're going to do an example that you all should have seen before on your homeworks, recitation quizzes, and everything like that. So we're going to use this table over here. This is our data of our reactions. And what I want you guys to solve for is, first of all, the reaction order. So the reaction order. Second would be the value of K. And then third is going to be your rate law. Okay? And just for
sake, again, you guys can come back and watch this video. I'm just going to walk you through the steps, but this will be posted so you can go do it on your own to make sure you know you're doing it right. So the first thing that we need to do when we're looking at one of these problems is we need to figure out the order of each of these specific reactants, because then we're going to get the full reaction order. So what we have to do is pick two experiments, and I made this problem up myself, so if the data looks a little glitchy, it's me. But what we have to do is pick a reaction where we can isolate one of the reactants, okay? So we need to pick two reactions where one reactant concentration stays the same and the other one changes. So let's solve for the concentration of B first. You guys should be able to eye this one pretty easily. What two experiments would you use to find the reaction order of B?
1 and 2.
1 and 2, okay? So these are constant, and these change. By what factor does this change?
4.
Okay, so this changes by a factor of 4. Now, if we want to figure out what this order is, we move over to our rate. Okay, so by what factor does this change? 4. Okay, so if this changed by a factor of 4 and your rate also changed by a factor of 4, then this reactant is first order. Okay, so that's one way you can easily eye it and do it. Now, we're going to solve for A doing the other way that a lot of you have done with the longhand way. So we move over to here. You guys have probably seen this equation. Rate 1 equals K1 over that, so your two rate laws over each other. And what you'll see here is we can actually start canceling stuff out. So what I do here is I can just pick two experiments and start plugging my rates and concentration. And then those are going to be 0.5 and 0.25. And then those are going to cancel again because those are going to be the same. So we cancel those, okay? So now we have, what's this factor? 8 equals what? 2 to the n?
Yes.
Is everyone with me there? 0.5 divided by 2.25? So we have 8 equals 2n. So then we can do log 8 equals n log 2 divided over, what does n equal?
3.
N equals 3. Okay, so coming back to our first one, what is the reaction order as a whole? 4. Okay, so what's our rate constant? Units. Yes, exactly. It's M, just the one that Braden just did, fourth order reaction. Okay, so now what we can do is we have our rate law, so now we can figure out the value of K, all right? So the easiest way to do this is to just pick an experiment and then just plug in all the information. So we know right now we have rate equals K, and then A was third order, and B was first order. Okay? So plug in all that information, and then you can solve for this K value. Right? Once you have that, then you can write your full entire rate law. This is something to remember on your test. If he ever asks you to write a rate law, K has to have a numerical value. Okay? So K is going to be a number with units. And then you're going to have your concentrations like this. Anyone have any questions on this? Sorry, I kind of glitched that. No? Okay.
Okay, so what he said was important about making sure you have an actual numerical value for your K. Now, if we're using, if you're not given an actual table full of data, we're going to get to this later. There's no way to get an actual number for your K value. Rather, you're just going to show it in terms of units and things like that. We're going to get to a problem like that a little bit later. So there's a couple other things we want to talk about really quickly. Is this about this problem?
Just real quick. So you said that when he says like to write the rate law,
Yeah.
we need to make sure there's a value for K.
Right. If you're ever given a table full of data, and with this table, part of the question says write out a rate law for this experiment or this reaction that's occurring, well, you have enough things to solve for a K, an actual number for a K, for the constant, so actually do that and include the right units. If you forget to, you'll probably dismiss half of the problem. We'll have to see, but you definitely won't get full credit. In other cases, wherever we're not given actual data, so we just show our K in terms of units and what our K represents, as we kind of derived it from the previous Ks in a mechanism. And we'll get to that, so that makes a little bit more sense, okay? Something that's important to understand, you guys, going along with these things, if you are given a question where you are first shown a graph of something in terms of the time that it progresses, and either a concentration, or it can be a mass, or anything like that, we're talking about rates. There are several types of questions that can be asked. I know that sometimes this is confusing. I drew a couple graphs here. Now, because we're kind of doing this on the chalkboard, we don't have the means, and I'm not a good enough artist to draw this in a way where our scale is perfect. But that'll be given to you, so you'll actually have the means to really solve for real numbers. What I'm trying to do here is show you how to solve for potential questions. So just keep that in mind as we're going through. Jot notes so that you can make sure you know how to do this. So what if you were asked, and you were given a graph like this? This is in milligrams, right? It doesn't have to be in concentration. This is milligrams and this is time. This is referring to a reaction. And you were asked something like, what is the instantaneous rate of this reaction? How do you solve for something like that? You're given this graph, you got this data, this line, what's the instantaneous rate? Well, how we do that is you look at it right when the reaction starts. And when it starts, it's what we call a tangent line. We're looking at the slope of what the slope was when this initially started. So we know that this starts to curve over the course of the reaction, but initially we have this speed or this rate, okay? So to solve for an initial rate, you want to find the slope of this initial straight line, okay? Just regular algebra, rise over run, y2 minus y1 over x2 minus x1 for 2 points on this initial straight line. That would be how to solve for an initial rate of a reaction, right? What if the question said something like, solve for the average rate of reaction for this graph? How do you solve for an average? You see that if it was an average, this would be easy, right? This one is straight. So the initial rate equals the final rate equals the average rate, right? It's all the same rate. But this one does not. So our initial rate is steep, right? Versus in the middle here, it sort of levels off. So how do we get an average? How would we do that? Anybody know?
The end concentration minus the beginning concentration over the time, and time minus the beginning.
Yeah. So what he's saying is you take this n value, right, wherever this stops, okay, and you take the beginning value, and you almost just draw a straight line to them, okay? And you do a rise over run for those 2 points. The slope between those 2 points where it ended and where it began, right? So the average rate is really just this, right? So that's how you would solve for that, using real numbers. Remember, rise over run, y2 minus y1 over x2 minus x1. Another type of question that can be asked is, what is the instantaneous rate at a specific time? Now, the initial rate is different, right? That's this initial. Instantaneous rate at a specific time, I could say, what is the instantaneous rate at 100 seconds? So what I would do there is come to 100 seconds here and do the same thing I did for this initial. I want to find the slope of where we're at about 100 seconds. And I know this maybe seems easy, but it isn't that easy sometimes to pick perfect numbers. Because you got to understand, I'm sure someone next to you, if they were to do this problem, might get something a little different than you. But you should all get something within a reasonable range that should be marked correct. So you kind of have to be exact with this and eye this correctly. Some people like to draw long tangent lines and pick very clear points that are out like this. I recommend if you ever had to do this, you use a straight edge or something like that. You would pick points out like this, right, and solve the rise over run of this specific slope. Other people like to pick points that are really close to this that will still have the same slope, right, as this. So you wouldn't want to pick this and this point, because what that would do is cause it to be like that, which isn't necessarily the same slope as something right here, right? So pick 2 points next to it and solve for the slope of that line would give you an instantaneous rate at that amount of time. Behind.
What would be like a reasonable point to pick, like 90 seconds, 95 seconds?
Right, so you could pick 90 seconds and 110 seconds. That's totally fine. That'll be up to you, and just use your best judgment. I recommend maybe do it 2 ways.
Okay.
Maybe see if you're getting the same value. If you keep getting bogus stuff and it's totally different, try to refine what you're doing. Just understand that you're solving for the slope of that specific segment, and that's what's important. Do you have a question?
If you're given data, can you just pick the 2 points on either
side.
Right, so if you're given data, we're kind of back to these types of methods, and it's totally different. You pick points on either side, right? But if you're given a graph, the reason I bring up a graph is because we haven't really seen stuff like that, and that's in the book. These are valid questions, and I don't want you guys who maybe have mastered kinetics, but have never really looked at a problem like this to get there and go, oh my gosh, I knew everything about rate laws, and I didn't get how to do this. And then maybe learn afterwards an exam or see later that it wasn't as hard as you thought it was. So something like that, I just wanted to bring this up. This is a good question to look at. So beyond that, let's talk about predicting a rate loss. So, Judson.
What are on the axis? What are they labeled?
So the axis here is labeled time on both. This one is in concentration, and this one is in milligrams. These two are by no means related to one another. I'm just showing you that you don't have to always have molarity as your axis. You can have mass. But what does that mean about your rate? Is your rate law, and you're looking at this graph, is your rate or instantaneous rate molarity per second? No, it's milligrams per second, right? So just make sure you're writing the right units and you're really aware of that. Okay? So let's do, this is a problem, you guys, that I feel like has given a lot of people grief. And I don't want, if this is on your free response exam, I don't want this to give anybody grief because it's something that you're all capable of doing. This was on our yellow sheet. This is a different one. I kind of came up with this one on my own. Again, I'm using hypothetical, just letters to represent species or molecules, right? But this is, I want to teach you how to solve a problem like this. This is an important one. This is one that I would suspect is one that you should know for this free response exam because this is important. This kind of incorporates several things we've learned from kinetics. So earlier, someone said up here in the front that when we're predicting rate laws, it's important to understand of a mechanism. What is our slow step? Well, from that last sentence I just said, there maybe were several words that we first have to define, like what is a mechanism then? You know, what does that mean? How do I know when something's a part of a mechanism? What in the heck is an elementary reaction? What is a normal reaction? How can I decipher between the two so I know what to do on a problem like this? So let's get this very clear, okay? Not every reaction you see written out has a mechanism, right? Some reactions are what we call elementary, meaning when I write that A reacts with B to give me C, literally A did react with B. Those molecules did come together to give me C. In some cases, I'm shown a reaction with A plus B gives me C, but what I realize when I look at the rate law given for that reaction, there are species written in my rate law that are not included in this main reaction, meaning that main reaction must be broken down into separate smaller reactions where I actually derive my rate law for this overall reaction to actually occur. What I mean is sometimes A doesn't actually react with B. Sometimes A reacts with D, which gives me E, which goes back and reacts with B, which overall gives me C, right? So there are mechanisms. Sometimes reactions occur as they're written, and sometimes they don't. They're broken up. So how do I know if it's a mechanism or not, or if it's an elementary step? Well, with my rate law. If I'm given a reaction, and then I'm given a rate law, and I'm saying, does this rate law correspond with this reaction? Well, just look at what you're given, right, and look at the rate law. If the rate law includes species that are not found as reactants in the reaction given, then those two do not correspond, meaning there must be a mechanism involved in elementary steps. So this is an example of elementary steps. You notice the first question is, well, what is the overall reaction? Because what I'm saying here is, these are two elementary steps that somehow come together to form what I would write out as my overall reaction. So quickly, look at this, write down on your piece of paper what the overall reaction for these two elementary steps would be, right? How we do that is we look at what I have as my reactants versus what I have as products, and I look at things that are across these reaction arrows, right? And I try to cross out things that are across. So B would cross out with B, right? I see my F would cross out with an F. There is no A's on this side, so A remains, and everything else that remains, I drop down. Okay? So my overall reaction for this should be A plus G, right? Those two, B and F, were gone. Gives me C plus D plus E. This would be my overall reaction. Okay? So, now it wants me to predict what is the rate law for this reaction knowing these elementary steps. So earlier it was stated, you're only as good as your slow step, which is valid. You're only as fast as your slowest player. So we know that our slow step is right here. When we're looking at that, what do you guys know about elementary reactions and writing rate laws?
Concentration of the order.
Loud. Someone just say it loud. Be bold. Let's hear it. What's something you know? There's several things. There's not just one right answer. You can't have intermediates. Number one, can't have them. What else?
The coefficient is the order.
Right, she said the coefficient is the order, meaning you can derive your rate law directly off your elementary step. So if I have a 2 here in front of f, that would be squared. Now in this case, we don't have any coefficients, right? It's just 1 for each one, so we're not doing any squaring or cubing, but she is valid. In the future, if you're given that, if there's coefficients, those go directly as your order for that species. Okay? So let's look at our slow step. This is where our reaction is occurring. Do we have an intermediate?
Yes.
Yes. Which one is it? F. Why is F an intermediate? Right, it was made in the first step and immediately used up in the second step, so there's no way that we can really measure that concentration without trying to stop time and look at how much F we have, right? So F is our intermediate. We cannot use it in a rate law, although this is our rate determining step. So that means in order to write a rate law, I have to solve for something that is equivalent to F, that equals F. Okay, and how I can do that is coming back up to my first equation here and solving for F in terms of these other concentrations. So I've written these double arrows, which means that a reaction is reversible. So it can go forward and it can go in the reverse direction. Okay? So if I'm going to solve for F, I know that the reaction rate going this way, using a specific K constant we call K1, is also equal to the reaction rate going this way, but using a different K constant, K reciprocal of 1, right? So the reciprocal of K1, or 1 over K1. Yeah?
Can the slow step have like equilibrium? I thought it couldn't. Only the fast step would be an equilibrium.
Okay, so yeah, most reactions are reversible, and our slow step, mostly just our fast step is like this. I just drew that, but yeah, your slow step is usually irreversible because of the way that the graph is so much activation energy to come back from it, so because it's so big it comes down. So that's valid. So here, right, we would want to solve for F, and to make this quick, right, because later you guys can go back and look at this and do it slow. Let's just make this quick. The concentration of F would be equal to K1 divided by K reciprocal of 1. We would have the concentration of A times the concentration of B, both are first order because of our coefficients, divided by the concentration of C times the concentration of D, right? F is directly equal to this. They're equivalent. So I can plug all this stuff in for my slow step right here. So to rewrite the rate law for my slow determining step, I just have to incorporate all that mess in for F, include G, and a new K. It's not K1 nor K reciprocal 1, we'll call it K2. Okay? We just have to name it. So my rate law would be rate is equal to K2 times K1 divided by K reciprocal of 1 times my concentration of G. Let's put that one in immediately. Right? Times whatever else F equals now. Because now that should be times F, so we're going to go times A times B over the concentration of C times D. Okay? So, this would be my rate law, written. So, a lot of people would ask me, what do I do with these? Can I leave them like this? Can I just write a new K? I've seen people just write a new K. Really, you can do both as long as you indicate that you knew what your new K is equivalent to this. If you just leave it like this, I don't see you getting marked wrong. This is still correct. But sometimes people like to clean it up. So if you were to rewrite it, you would just write rate is equal to K, and then just somewhere off to the side indicate that you know that K is equal to this, right? That you understood this part, that K was equal to that. And then this would be your rate. Go ahead.
Now, are C and D not intermediaries?
No, they're not intermediates because they're not actually used up. Right? They're just formed, but they're not used up. Right? So you'll notice that my main reaction that I've written here still produces C and D.
Oh yeah, you're right.
Yeah, see what I mean? So they're not used up, so we got to include them. Any questions about this? This is a problem I know has eluded people in the past with whether or not you can include things in the denominator for a rate. We haven't seen that a lot, but you can. That's totally valid. Include concentrations in your denominator. Correct?
What if the rate determining step is on top?
If your rate determining step is on the top, that's a good question. Well, you probably don't have an intermediate
Kind of like a conceptual question. If the rate of the slow elementary step equals the rate of the overall reaction, why do you have to put it in different terms? Why can't you just leave it as that? Why do you have to take the intermediate out of the picture? You know what I mean?
So the reason we cannot include the intermediate is because these rates are dealing with concentrations, right? If you look at the rate law, we're talking about a concentration, but if I'm making something and immediately using it up, there's no way to measure how much of it I'm making, how much of it's being used and being used, because it's being made and now it's gone. There's no way to measure it, so I can't include those values into my rate law, because what a rate law does is it allows me to plug in concentrations of things and determine how fast that might go. But with F, because it's made and gone so quick, it's not a value that I can use in my rate law, right? So, okay, let's keep the chatter down just a little bit, and let's answer this question right here. What is F? We talked about it, it's our intermediate. What is B most likely? A catalyst. I love it that you guys had that. Okay, I thought that would get you guys. No, it's perfect. Why would you say it's a catalyst? Right, say it loud. Say it one more time loud. It's not changed, he says. Okay, so it was also used in our fast step to produce a fast step, right? And then it's not changed. So, that one. Okay, so.
Sorry, could you clarify what you mean by is not changing?
So B, we're not forming it and then using it up to change it into something else, right? It's not written in my overall reaction, but B just remains B the whole time, versus F is made and used up, chewed up and used, right? As something else. Okay, we have a lot of hands for this. Now this is something that we should talk about after we finish the rest of this. You can go over the video later. And let's do your specific questions at the end, okay? Don't want to shortchange anybody. We just gotta keep this going with the amount of time that we have, okay? Alright, let's see. Let's finish this up. I have two more things to talk about, and then we're going to jump into radioactivity really quickly. What is the molecularity of this reaction? Right here? Bimolecular. Because we had two things that came together, okay? So that leads us into something called the collision theory. Who knows what the collision theory is with reactions? This is an important one to know. Right here at the front, say it loud.
The collision theory is the idea that molecules have to collide at a certain speed, like a certain minimum speed,
Okay.
and at a certain orientation for them to actually react and form products.
Exactly. She said, if you couldn't hear that, the collision theory is that molecules have to collide first at a certain speed, meaning a certain energy. They have to hit at a certain energy. And at the right orientation, right, for this reaction to occur. So the collision theory usually has three things associated with it. Number one, for a reaction to occur, the molecules have to collide. That one's pretty self-explanatory. They have to hit each other. They have to come in contact, number one. Number two, not only do they have to hit each other, they have to hit each other with enough energy or in enough energy, so if the temperature is really high or something like that, to overcome the activation energy for the reaction to occur, okay? And number three, what did you say the third one was? That they have to be oriented correctly. Perfect. So they have to be oriented, meaning if there's a certain orientation that those molecules have to be in, where a lone pair of electrons might attack an orbital from another molecule, they have to be oriented correctly for those things to occur, right? And you'll realize later on in your chemistry careers in OChem that these are really valid things. There are certain orientations and things that are important, right, for how things attack. So know the collision theory thoroughly, so that if you're asked a question, you can talk about the collision theory because you know it. Okay, that is it with our kinetics. Now, I know that there are plenty of other problems of solving using first and second order equations. A lot of that we did on our multiple choice exam. These are the things we think were most pertinent for the kinetics of this free response exam. If you have more questions, let's talk about it after, okay? Alright, so kind of switching gears, we're going to come over to radioactivity. There's a few things I want to talk about first, just conceptually understanding the belt of stability. Okay, so in our belt of stability we have protons on our x-axis and neutrons on our y-axis. So if you understand this belt of stability, all of these different types of decay should be very clear for you. So the first thing I would do is copy this into your notes. If you just have a picture of this, and you can see what happens in different areas of the belt of stability, it'll be a lot more clear for you when you get in there on your exam. Okay? So, first of all, positron emission and electron capture
basically do the same thing, okay? They're going to move us in the same direction. What Dr. Macedoni stressed in lecture is that positron emission has a higher tendency to happen when it's lower on the belt of stability. So if you remember on your recitation quizzes, you guys had a problem that was like 10 carbon, and what we wanted there was that you knew it was so far down on the belt of stability that to get back to a stable isotope, it would do positron emission instead of electron capture. With that being said, there's no definitive line that says, here's positron and there's electron capture. So if we're looking for something specific, it's going to be either up towards the top of the belt of stability or down towards the bottom. Okay? Next is beta decay. Alright, beta decay is when you're above the belt of stability and you're moving down in this direction. You're losing neutrons and gaining protons. Okay? And then alpha decay, you just have to remember, it's for any isotope that's over or equal to 84 protons. And the reason that is when you get so high on here, the belt of stability, what you want to do is come down really quickly. So the best way to do that is with each alpha decay, you can lose 2 protons and 4 neutrons. So you're coming down really quick. And that's why alpha decay always happens 84 and above protons. Yeah?
You have the electron capture arrow like kind of above the 84, is that?
Oh no, it's just in general. Just know that electron capture happens higher up on the belt of stability. Okay? Alright, let's go through these then. So alpha decay, what does alpha decay do? Emits a helium, okay? And I'm going to have to look up, I wrote these down. It's going to make 208, yeah, lead. And again, these are just examples. I'm not saying that polonium-212 is going to do all of these. It's not going to. I'm just keeping the same example consistent throughout so you can see what would happen to the isotope that's made. Okay, so beta, what does beta do? Yep. And that's 212, 85, AT. Okay, and again, if you think about this beta decay, what happened? We gained a proton, right? So if we come back over here, we can think about this conceptually. We're moving in this direction. Okay? We're gaining protons and moving in that direction on the belt of stability. Okay? Positron emission. What a positron is, it's a positively charged electron. That's the easiest way to think about it. So positron emission, it's emitting a positively charged electron. Okay? So you have 0, 1, E, and that is going to make 212, 83, BI. And then electron capture, remember, does the same exact thing. So we know this is going to be 212, 83, BI. And what this does is it basically captures an electron is the easiest way to think about it. Yeah?
Do we also need to know neutron capture?
Neutron capture? Yeah. Yeah, I would know that. These are just the main ones that were on this. We just want to review these. Again, yeah.
I was just wondering when we use neutron capture.
So neutron capture is we're going to talk about it. It's kind of like fission. When you shoot a neutron at something, and then it can create a fission reaction. All right. So the next thing I wanted to review first, let's just talk conceptually about Einstein's equation. Okay? We have E equals mc squared. All right? What is E? I wrote it up here. It's the nuclear binding energy. So what the nuclear binding energy is the easiest way that I like to think about it is, let's say we're using this example used up here, 212 polonium. Okay? So let's say we have a bucket of protons and neutrons. All right? So when you're calculating your mass defect, what you're comparing is the hypothetical weight of all those protons and neutrons versus a real nucleus. Okay? So let's make it easy and say carbon 10. So carbon 10 is going to have 6 protons and 4 neutrons. So what we can do here is calculate this hypothetical weight. We know the weight of each proton and each neutron. So we can say, hypothetically, this is going to weigh this much. But what we see in reality is that when that nucleus forms, it's actually less of a weight when it binds together in a nucleus. So we have the same amount of protons and neutrons here, but the weights are different. And the reason that is that when your protons are positively charged, and when they normally repel each other, but when they get close enough, they can actually stick. And when they stick to each other and form that nucleus, what happens is your system actually goes to a lower energy state, and with that, energy is released. Okay? So that energy released, what Einstein figured out is that energy released actually has some form of mass. Okay? And so that is what our mass defect is. It's the difference in what we think it should weigh and what it actually weighs. Okay? That's the nuclear binding energy. The nuclear binding energy is that energy released when those protons come together. Alright? So what we can do is calculate this through that equation. Does anyone have any questions on this? Yeah. Let's just do like 2. Go ahead.
We don't throw in the weight of the electrons, do we?
So that's a good point to bring up. So in here, I didn't include the electrons, okay? But let's say on a test question, they said a carbon-10 atom weighs X amount of AMUs. What you have to calculate in there is that you have electrons, okay? So I only have protons and neutrons here, and if they say this is the total weight of my atom, then I have to subtract my electrons out, so I'm only comparing protons and neutrons to protons and neutrons. Yeah, in the back.
I think I understand mass defect. The thing that confuses me is fission is kind of the opposite. You explained in the review a couple of minutes ago how the massive
This value in this equation, okay? So if they say something went from 100% to 60%, then we know this ratio is 0.6. You can just do 60 over 100 is the easiest way to do it, okay? So then you can use that ratio to solve for different parts, and you can solve for the time elapsed or the half-life, or you can interchange those equations. Okay? Anyone have any questions on that, on those equations? Yeah. I'm sorry? The middle one is so there's 2 ways you can solve problems. Dr. Macedoni mentioned this in class. This is a new equation that's in this new book, and so you can use either. So this equation right here, it kind of incorporates both of these together, or you can use both of these. It's just whatever you're more comfortable with. I would just go with what you've been doing. Okay, so now let's hit on fission and fusion. Okay, what is fission? Go ahead.
It's like an atom or a nucleus, like starting as a bigger mass, and then like something goes in and splits off and turns into smaller masses.
Exactly. So what fission is, like he said, you're going from something bigger to a bunch of things smaller, okay? So fission is bigger to smaller. And how this normally happens, you're probably going to want to be familiar with it. So let's say we have a neutron right here. What we can do is actually shoot that at a mass of something, okay? So think about the atomic bomb. They had to have that critical mass there for this reaction to work. So what you can actually do is shoot a single neutron at a critical mass, and what happens is this will actually split up into 2 nuclei, and 2 or 3 neutrons will also bust off from this. And those 2 or 3 neutrons will hit 2 more of these. And then those will hit those. And then those will hit those. It's a chain reaction. So every time you hit it, you're creating new isotopes, which will be smaller than the one you started with. And you're also emitting neutrons, which those neutrons go and then hit other isotopes. And then they break, and then they break, and then they break, and a huge amount of energy is released. Now, fusion is the exact opposite. Fusion is where we're going from 2 small things to 1 large thing. And this, yeah, go.
Sorry, which one is it? Fission or fusion, where the products weigh more than?
That's fusion.
Fusion.
Yeah, that's what we're talking about. So fusion is you have 2 small isotopes, and basically what you do is you smash them together, you combine them, and it makes a larger isotope. So it's the exact opposite of fission, okay? And the reason, so fusion, it happens on the sun, one thing to maybe note is that it's really hard to reproduce on the Earth because it takes such a large amount of energy to combine those into a larger isotope. It's just really hard to reproduce on the Earth. So that's just one thing to know. Does anyone have any more questions on fission and fusion? Go ahead.
How would we be tested on fission and fusion?
He could ask you, like, what is fission? Or what are the differences between fission and fusion? So just be able to know this well enough to compare and contrast